Hello guys, so in this video we're going to go over how to apply the direct comparison test given a series. So when do we apply the direct comparison test? So we apply the direct comparison test whenever the divergence test fails. So the first thing we're going to do in step 1, as we do for any series, is we're going to go ahead and test that divergence test. So we're going to apply the divergence test. So in doing so, whenever we apply the divergence test, which I'm about to do right now, the divergence test is basically just taking the limit as n approaches infinity of the function, which is 4 divided by n squared plus 7. And in doing so, whenever we take the limit, we're going to go ahead and plug in infinity wherever we see n. So 4 divided by infinity squared plus 7 is equal to 4 divided by infinity. And 4 divided by infinity is equal to 0, because any constant over 0 is 0. So now that we know that it passes the divergence test, the next step we're going to apply in step 2 is we're going to identify. So now that we know that, we're going to attempt to apply the divergence test. So in doing so, whenever we apply the divergence test basically is, or divergence test, apply the direct comparison test. Direct comparison test. So in doing so, whenever we apply the direct comparison test is basically just finding a series that's very similar and comparing it by finding out that whether the larger series converges or the smaller series diverges. Then if we can find out either or, then we can basically find out whether the whole series converges or diverges. So in this case, for the next step, we're going to go ahead and identify, which I'll call step 2. We're going to identify a similar series. And now how the heck are we going to do that? So we're going to identify a similar series by simply just removing the insignificant terms. So in doing that, what is our series right now? Our series right now is, we're going to call it f of n. F of n is equal to 4 divided by n squared plus 7. So what do we mean by removing the insignificant terms? So what I mean by that is which one of these 3 terms contributes the least to the series, to the value of the final series, of the final sum of the series. So we can definitely say it's the 7, because the 4 scales it up and the n squared is what determines the series. So the 7 is what is the least significant term. So in this case, we're going to identify a similar series, which is going to be 4 divided by n squared. So now that we have 2 series, in step 3, the next step that we're going to take is we're going to identify, for step 3, we're going to identify a smaller a sub n, smaller series a sub n, and larger series b sub n. Why? Because to directly compare them, we want the larger one to be b sub n. So that way, if it converges, then a sub n also converges. And vice versa is true. If the smaller one diverges, then the larger one has to diverge as well. So in this case, I'm gonna go ahead and underline step 2 because it's also an important step. So now that we have that, which one is our a sub n? So we can test this out by simply just testing to see which one is larger. We can test which one is larger by simply plugging in 1, or whatever your n value is. But in this case it's 1, in most cases it's going to be 1. So in doing so, we're going to go ahead and do this for both sides, for both f sub n's. So f of 1 is equal to 4 divided by 1 squared plus 7. And on the other hand, f of 1 is equal to 4 divided by 1 squared. So what does the first one on the left hand side equal? The one on the left hand side equals 4 divided by 1 plus 7. So this one's equal to 1 over 8. There we go. And then this one equals simply 4 divided by 1 squared, so that's 4. So clearly, our b sub n is equal to the more simplified function, which is 4 over n squared. So now that we have that, so we know a sub n is equal to the smaller function, which is 4 divided by n squared plus 7, and the larger function b sub n is equal to 4 over n squared. So now what we're going to do is, for the next step, now that we know a sub n and b sub n, in step 4, we're going to go ahead and test the simpler series. So in this case, the simpler series comes out to be b sub n. So we're going to go ahead and test the convergence or divergence of b sub n. So knowing that b sub n has the form of a p series, we're going to go ahead and apply the p series. So apply p series. So what is a p series? The formula of a p series is one divided by n raised to the p. So in this case, we have 4 divided by n raised to the p, but we only really care about the p and the n. We don't really care about the constant. So our b sub n, the series of b sub n, as n equals 1 and is approaching infinity, is equal to 4 is equal to the series as 4 divided by n squared. And what's our p? Our p is simply equal to n. So p is equal to whatever the exponent is on n. So in this case, n is equal to 2, so our p is equal to 2. applying P series, which I will underline. So by applying P series, noting that P is greater than 1, we can therefore infer that our P that this whole series is going to go ahead and converge. Why? Because that's just the properties of the P series. If P is greater than 1, converges. It converges. P is less than 1 or equal to 1, diverges. So I'm just going to leave this off to the side. So in this case, P is greater than 1. So this whole problem converges. So this is only part of our answer. So now the whole answer. So what does B sub n say about A sub n? So right here, we have these direct comparison test conditions. So since B sub n converges right here, what does that say about A sub n? A sub n also converges, because when the larger one converges, the smaller one has to converge. So for your final answer, you want to state it something similar to this. Yeah, we have a lot going on here, but this is our final answer. So since the series B sub n converges, since the larger B sub n converges, the smaller A sub n also has to converge. Then the series A sub n also converges. And that's how you apply the direct comparison test. So basically just apply these steps, these 4 steps, to basically we're comparing it to a similar function. So in quick retrospect, the first thing we did was just apply the direct comparison test to see if it was inconclusive, and it was, because it equaled 0. So it failed the direct comparison test, or the divergence test. Then we apply the direct comparison test by identifying a similar function. And then in doing so, in step 3, we identified which one was which one was A sub n and which one was B sub n. And we did that by simply just plugging in n equals 1. And in doing so, we got 4 and 8. So A sub n is 4 divided by n squared plus 7. The original series, B sub n is 4 divided by n squared. And then from there, all we simply did was just test the simpler series. And in doing so, we applied the P series, and we got P is equal to 2. So P was greater than 1. And whenever the P is greater than 1 in a P series, then that series converges. And since B sub n converges, A sub n also converges by direct comparison. And that's something I forgot to write. So it converges by direct comparison. So let me erase this. It converges by the direct comparison test. So that's a lot of words, but it's always good to write it. And that is the final answer. Thank you for watching. I hope that was helpful. Hello guys, so in this example we're going to go over how to apply the direct comparison test for this particular series. So we're prompted to find whether the series converges or diverges. So the first thing we do is for step 1, we're just going to go ahead and simply just, as we do for any series, is we're going to apply the divergence test, because that's always the first test we do no matter what series we're looking at. So I'm going to go ahead and try out the divergence test to see if that works, because sometimes it does work and it'll eliminate a lot of work for us to do in the near future. So in this case, so we have a series as n starts at 1, is approaching infinity, of 9 plus n plus 9 divided by n squared. And according to the divergence test, we can basically just take the limit as n goes to infinity. So the limit as n goes to infinity would just be a matter of plugging in n, would be plugging in infinity for both terms, and whenever we do that, we simply just apply L'Hopital's rule. And when we apply L'Hopital's rule, we get the limit as, taking the derivative of the top and the bottom, we get 1 over 2n. So when we compute this limit, whenever we plug in, we get 1 divided by 2 times infinity, which is simply equal to 1 over infinity, which is simply equal to 0. So therefore, we have passed the condition for divergence. So now what we're going to do in the next step is, now that we know it passes the divergence test, we're going to attempt the direct comparison test. And we're going to do this simply by, for step 2, we're going to apply the direct comparison test. And whenever we do that, all we're simply going to do is we're going to compare it to a series that's very similar. So I guess I'll call it step 3. So for step 3, we're going to compare it to a series that is very similar. So here we have our series, which is n plus 9 divided by n squared. And then we're going to call this f of n. And a series very similar, we can go ahead and identify it by just simply removing the insignificant terms. So the insignificant term here, I think, is obviously the 9, because it has very little to do with the series, how the series turns out in comparison to the n's. So in this case, our f of n is simply just going to be, the other series we're going to compare it to is simply just going to be n divided by n squared. Okay, so these are our two series. So now for step 4, what we're going to do in step 4 is we're going to identify the smaller a sub n and the larger b sub n. And in doing that, whenever we identify the larger a sub n and the smaller b sub n, we will then have two series and we know which one to compare as the larger and which one as the smaller. So in this case, the best way to go about this, and I'll leave a note right here, the best way to find a larger series is just to plug in 1 by plugging in n equals 1 into your series. And whichever one is larger is your larger series. So I'm just leave that note. And that's what we're going to go ahead and do, is we're going to go ahead and just simply plug in 1 for both of these. So f of 1 is equal to 1 plus 9 divided by 1 squared, and f of 1 for the other series is equal to 1 divided by 1 squared. So in this case, whenever we plug both of these in, we get f of 1, 9 plus 1 is 10 divided by 1. So this first one on the left hand side is equal to 10 over 1, which is simply 10. And on the right hand side, we get f of 1 divided by 1 is equal to 1. So we can clearly see that this one is larger. So this one's going to be our b sub n, and this one's going to be a sub n. So now that we've identified them, we're just going to quickly take note of which one's which. So down here, we're going to take note of our a sub n and our b sub n. So a sub n, b sub n. So our a sub n, the smaller one, would be this one on the right hand side, which was n divided by n squared. And on the left hand side, the larger one is n plus 9 divided by n squared. So now that we have both, the next step that we're going to do in step 5 is we're going to test the convergence or divergence of simpler series. So we're simply testing the convergence or divergence of the simpler series. So which one of these two is the simpler one? N over n squared or n plus 9 divided by n squared? So it's clearly that one. So we're going to go ahead and test the convergence of that one. So the convergence of a sub n, which is n over n squared. And keep in mind that we can rewrite this as n to the 1 divided by n to the 2, n raised to the second power, which would simply be 1 over n. And this right here is a p-series because it has the form of one over n raised to the p power. And in this case, 1 over n, p is 1. And whenever p equals 1, the series diverges. This is also known as the harmonic series. So since p diverges, a sub n diverges. And since a sub n diverges, the smaller here, I'll leave room for this. So since the smaller a sub n diverges, the larger b sub n will also diverge. Why? Because I'll draw it out for you real quick. So we have, let's say for example, we have a series Let's say we have series A sub n, and we have another series B sub n. Whenever the smaller one converges, whenever the larger one converges, the smaller one converges, or vice versa. If the smaller one diverges, the larger one has to diverge. And how do I know this? I also could have known this just by knowing the conditions of convergence for P series, which are right here. So notice how whenever the smaller A sub n diverges, the larger B sub n also diverges. And whenever the larger B sub n converges, the smaller A sub n converges. So in this case, the smaller A sub n diverge by harmonic series, or 1 over n by P series. So therefore, the larger one also diverges. And that's how we apply the direct comparison test. So step 1, apply divergence test. If it's inconclusive, which it was in this case, then we apply the direct comparison test. So we compare the series to a very similar series, which we did here. And how do we do that? Which I'll leave a note right here. We do that by removing insignificant terms. Insignificant terms for direct comparison test. So that's how we do that. And then from there, once we figured out what our other series, similar series was, we identify A sub n and B sub n by just plugging in 1 to see which one's larger. Then we identified A sub n and B sub n. And then we test the simpler of the two series, which in this case it was A sub n. And then we applied the P series, which I forgot to write. So I'm going to go ahead and write it real quick. So apply P series, because that's what we did essentially right here. And in doing so, we found out that P is equal to 1. And in this case, when P is equal to 1, I'll write the conditions real quick. When P is greater than 1, converges. P is less than or equal to 1, diverge. Those are the conditions for a P series. These right here. And then from there, we were able to tell just based off applying the direct comparison conditions, since the smaller A sub n diverge, the larger B sub n also diverge, as I showed in this graph right here. Anyways, that's all for this video. Thank you for watching. I hope that was helpful.